the aircraft is in symmetric maneuver, whether it is a level flight or a dive or anything, what is the aeroelastic effect during that particular condition? Because we have seen that because of the twist deformation of the wing, your angle of attack is changing. And when the angle of attack changes, again the load is changing. Okay. So in this problem, if you consider the aircraft wing as a rigid one, you will get one load distribution. The moment you consider the aircraft wing is flexible in twist, you will get a different load distribution. And then you need to get what is the new load distribution due to the deformation of the wing and what is the flight condition. So the flight condition is, we say, symmetric flight. Okay. And in this, you need to know, suppose there are two types of problems one can always look at it. Given the initial angle of attack, that we call it rigid angle of attack, what is the load factor I am going to generate? The second problem is, given the load factor, what should be my rigid angle of attack? Because load factor is basically, it is related to how much it is going to lift. Lift by weight is my load factor. Okay. Now, how much angle of attack I must give, which also takes into account the elastic twist of the aircraft, because this is very important. If you want to go in level flight, you must know what should be the angle of attack of the wing before elastic twist. After the elastic twist, the net will be equal to the weight of the aircraft in level flight. So there are two types of problems that exist. But to solve that, we consider the symmetric lift distribution, and first we take the uniform wing. Please understand, only for uniform wing you can get a closed form solution. If it is not a uniform wing, you have to go for the Galerkin or Rayleigh-Ritz type of solution. Okay. So we will take a closed form solution for uniform wing using strip theory again. Okay. Now the moment I write it as a uniform wing, my torsion equation of motion is, you know, that d over dy of Gj and then we wrote plus QEC, we put CL alpha into theta equals minus QEC CL alpha alpha rigid, which is the initial angle of attack of the thing. Then Q C square C MAC plus N MGB. Okay. Now if I take uniform wing, I can divide by Gj everywhere. Okay. I can write this equation in a very compact form, which is written as d square theta over d y square plus okay, I will write where lambda square is Q E C C L alpha over Gj and your Kr is nothing but 1 over Gj multiplied by Q E C Cl R. R, in other words, CLR, instead of CLR I will put it Cl alpha R plus Q C square C N A C minus N M B D. Okay, this is my in a short form, because uniform wing, please understand, I am taking the uniform wing, that is why it is coming out like this. Now I have to get the solution of this. The solution is this, a second order equation with, please understand, if it is uniform wing, I can write a closed form solution. If the wing is not uniform, that means all these E, C and CMAC, everything can change along y-axis, even M, D. All these properties are functions of your span. Then in that case you can get only approximate solution. Okay. That approximate solution we learned last class. Either you can use Rayleigh or Galerkin approach. Please understand, you have to use one of those techniques to get the solution. Otherwise, uniform wing we take, we will be able to write a closed form solution. For this problem, we will use it as a uniform wing. Okay. Now my general solution for this is going to be theta, which is a function of y, will be A sine lambda y and then B cosine lambda y, sine lambda y plus B cosine lambda y. Since these are all constant, because uniform wing, this is not a function of y, so your solution will be plus over lambda square. Okay. Now you can find out the constants A and B by applying the boundary condition. Boundary condition, you may say theta at 0 is a fixed end of the wing, and at the free end you will put d theta over dy at L. This is 0. Okay. Now you apply this boundary condition. When I said theta 0, 0 means this term is 0. So B plus KR over lambda square is 0. Therefore, this gives me the condition B equals minus KR over lambda square. Okay. Then here when I go theta prime, this will be A lambda sine becomes cosine, so you will have d theta over dy at L is essentially A lambda cosine lambda L. This cosine is going to become sine with a minus sign, so minus B lambda sine lambda L equals 0, because this is a constant. So you get A becomes, A is essentially B tan lambda L, and B is minus K over R, so you will get minus K, not K over, KR over lambda square tan lambda L. Okay. Alright. Now I can substitute and get my solution for theta y, which is, I will write it here. So so that this solution we will be using it later. Okay. You will write your solution as zeta, which is a function of y, becomes, because k r over lambda square, everything is sitting there. Okay, so you can take out common lambda square 1 minus, because you can say A is kr over lambda square tan lambda l. So we just put that tan lambda l sine lambda y minus cosine lambda. Okay, and you know what kr is. Kr is given here and lambda square is given here. So we will keep it, I will write here so that it kr becomes minus 1 over gj qec cl alpha rigid plus q c square cmac minus n mg d. And your lambda square is QEC CL alpha over beta. Okay. Now I have got the elastic twist due to the rigid angle of attack, and of course the aerodynamic moment and then the load factor. Now this is where I have two types of problems. I mentioned it. I erased this part and okay. Now what we have is, one is given n, given the load factor, what should be the alpha r. Another one is given alpha r, what is the load factor? Okay, load factor n. Because this is like wind tunnel test. Because in the wind tunnel, you mounted your model, if it is an aeroelastic model, please understand, not a rigid model. If it is an aeroelastic model, you put the alpha r given that angle, what is the load factor you generate? The other case is free flight. Because you are not going to say that if you want what is the load factor, like level flight, n is 1, because n should be equal to the weight of the aircraft. Then you must know what must be my alpha r. Okay. Now these are the two types of problems which will come in the aeroelastic calculations. Why we need to do that is, if you set any angle as a rigid alpha r, because of the flexibility, your load distribution is going to be different. Okay, because of the wing twist, the lift distribution will be different from if the wing is not elastically twisting. Okay. Now if the load distribution, because of the changes, that means your sectional bending moment, shear, everything will change. If that changes, your structural design will change. Okay. That is the reason you need to do aeroelastic calculation for structural analysis. See, traditionally, this is a very interesting statement which is made. Aeroelastic issues are treated only for to satisfy the certifying agency. Okay, because after you design your flight vehicle, it needs to get a certification like civil aviation or military certificate. There you have to demonstrate that this is fine. It doesn't have any aeroelastic. But today, the aeroelastic problems are becoming a design problem. Okay, you need to take the aeroelastic effects in the design aspect itself to have a very efficient, high performance aircraft. Rather than saying I will treat the entire aircraft as a rigid aircraft and then design my structure. And then I will take care of the aeroelastic problem at a later stage. If there is a problem, I will modify it just to satisfy the certifying agency. Okay. On the other hand, these days you are highly flexible, highly maneuverable, various types of aircrafts are coming, and even unstable aircraft they try to design such that it is stabilized using closed loop control. Then your wing flexibility plays a major role. Okay. That is why the aeroelastic problems assume importance in the design phase itself. Okay. Now, how do we solve these two problems? Basically, that is the basic question mark. We have obtained for a uniform wing. Please understand, this is for a uniform wing. If it is a non-uniform, you will again get the solution using approximate methods. I got the elastic twist distribution due to, you see, Kr. Kr contains rigid angle of attack, moment load factor, which means the twist depends on my load factor as well as this. Now my load factor depends on what is the lift. So what I have to do is I will write an expression, what is my load factor. I will take half wing of the diagram. Half wing means half the aircraft. So weight I am distributing into 1/2 of the wing. So W over 2 into load factor. This is what W is the weight of the aircraft. Please understand, this is not weight of the wing. This is weight of the aircraft, N is the load factor. This is what is to be supported by 1/2 or one wing. This must be equal to, you say Q, which is the dynamic pressure, into, you will put 0 to L, card, then CL alpha times, you will have alpha R plus theta Y, plus theta, which is a function of Y. So dynamic pressure, card, lift coefficient. Okay. Now the lift coefficient has two parts. One is the rigid part and the another one is due to the elastic twist part into dy. Okay. Now what you have to do is you go substitute the theta y here. Okay. Now when you substitute, you know that theta y is a function of alpha r and n. You follow? Therefore your right hand side, left hand side you have n. Right hand side also you have n. That means the load factor is a function of load factor. What you do is you have to gather the term on the left, then write n as the rest of the terms. Okay? And this, because we have considered uniform wing, I can perform this integration because CL alpha, everything is constant. So it is easy for me to integrate. But if it is not a uniform wing, you have to use approximate methods. Numerical integration you have to resort to. Okay? So that is why this problem, the moment you go to real problems, you need to apply numerical methods. That is why Rayleigh or Galerkin first to get this solution. After that you put them here, then you have to do numerical integration and then get the load factor in terms of your alpha r. Okay. So what I will do is, I will not go into the algebraic details, because the algebraic details are essentially you take this term, put it here, okay, after that you substitute for kr. Please understand, you have to substitute for kr here and then multiply the whole thing. Is it clear? It will be a little lengthy, messy expression. Alright? What I thought was, I will not write that in the board. I will finally go and then give you the closed form solution after integration. Okay? Because this part is just the algebra. Okay. But this as an exercise you can do it. This is becoming n equals QC CL alpha alpha r tan lambda L over lambda L minus C CM AC over E into 1 minus tan lambda L over lambda L, divided by W over 2L minus M G D over E 1 minus tan lambda L over lambda L. Okay. Now this is your uniform wing solution. Please understand, I have skipped basically the algebra, the steps involved in the algebra, because I don't want to write, otherwise I will be writing only the algebraic equations. Uniform wing, I take this term, substitute here, substitute for kr and whatever lambda, and then I integrate over 0 to L assuming uniform properties. Then I gather the n terms on one side and then I get this. Now you see, this problem you can actually solve both these things, both the problems. Okay? Both of them you can solve. If you are given n, okay, that means this is given. You don't know this. Okay, all the other quantities you know. So given this, you can get this. Once you get alpha r, okay, you can go back, substitute here alpha r. Then you get the kr. Okay, then you can put it here. Then you can get theta y. That means now I have alpha r plus theta y. So I can go and get the load distribution, how my lift is varying along the span. Okay, that is very important for my design. On the other hand, if I specify given alpha r, that means I know this, and I have to find out, because of course you have to know the flight condition. Please understand that Q is, every Q you have to take. That is why this will change for every dynamic pressure. The dynamic pressure is not You are solving, that is a given quantity. For every dynamic pressure, what happens? Now this is like a iterative loop problem. Every dynamic pressure, that means every flight condition, you need to solve this. So this is why this is a very interesting problem. Just to get load distribution on the wing, okay, and you get the deformation also. But please understand, this is the torsional deformation. But you are getting load distribution, but that is for designing for the bending problem. Please understand. Because you take a wing, you want to design each section. Your load is changed. Therefore the bending moment, shear, everything will change. And then you design your new cross section. When you design your new cross section, your GJ is changed. Okay? Even though you may have and your location of elastic axis, location of mass center, everything can change. You follow? That is why it is an iterative process. You cannot just say one shot solution, you take it. Because once you design, then you again recalculate, and this you have to do for various flight conditions. That means you basically in the design you take critical flight condition and design for that. After the rest of the flight conditions, you simply take whatever is the E and D, and then you get the load distribution. Okay? Is it clear? So with this is a symmetric loading. Alright? And please understand, even this simple problem is a little complicated. It's not very straightforward problem. Now we go to the next case, which is actually the anti-symmetric lift distribution. Because we have done symmetric, now we need to know anti-symmetric. Okay. So what I will do is I again erase this part, but here I will use a slightly modified symbols. Okay. Is this clear? This is for uniform wing, what to get below. But the intermediate algebra, I would say you fill it up. Okay. Now let us erase this part. We will start a new section, which is the anti-symmetric lift distribution. Okay. This is when you deflect your ailerons, because what you are doing, you put one aileron down, another aileron up. Basically you are changing the lift on the two sides of the wing. So I will draw one simple diagram. This is my x-axis and this is my wing. I am taking uniform wing, please understand. Okay. And I have this is my aerodynamic center and this is my center of mass line and this is my elastic axis as well as my y axis, and this is the distance, we call it E, and this is the distance D, and this is my y axis, this is my z axis, this is my x axis, and the wind is coming in this direction U, and you have a twist which is at a function of y. Now I have to put some control surface. So I draw a simple this angle is okay beta. Okay, I will erase this part. Okay, this is the beta deflection, and you can take this as L1 and the wing, full length of the wing, and up to this point you have another L2, maybe full length of the wing you can take L, please understand. You will have the aileron is only over L2 minus L1, only this distance, and where it is kept, that is also equally important. That is why you have plotted L1, L2, etc. Okay. Now, when you deflect the aileron, what happens? You are assuming first the wing is rigid. Wing is rigid means you are changing the camber of this particular section. Only this section, assuming 2D strip theory, there is nothing beyond. You are not taking 3D effects and other things. When you take this, I am changing the camber. So, my lift is changing. Okay. So, one is just the deflection of aileron is equivalent to changing my camber line or angle of attack. That is the first one. Next is because I am changing my lift, so I can generate a twist also. So that is a secondary effect. And on the top of it, because you have deflected, the other side also will deflect up. So one side load is increasing, another side load is decreasing, so the aircraft will start rolling. So the rolling will be, this is the roll rate I am taking. Okay? Because initially you will get a roll acceleration, please understand. Because when you deflect, initially it is flying. What happens? You change lift on both sides, there is a roll acceleration will come. The acceleration will go and change the load factor. Okay? Please understand, because the load factor, what is it? We took it as, actually, we say lift divided by weight. We take it as the load factor. But actually, these are all related to acceleration of the whatever mass of the element. Okay, that is why the load factor, when I start rotating, I am going to change my load factor on the wing. Okay. Now, how do I treat this problem? And another important point is, because of this P, this is the roll rate. What happens? The wing is going to go up, which means I am going to get a normal component of velocity on the wing, and that will change my angle of attack. Okay. So I will have my angle of attack if I want to write how angle of attack at any y. Okay. I am writing alpha y is the angle of attack at any y. This will have basically three components. I am writing it as three components. One of the components can exist, need not exist. That is delta alpha rigid. Please understand, delta beta times beta. Because this will exist only in this section. Other sections, because there is no beta here in these sections. Therefore, you cannot change the camber. So this is basically from the aerofoil characteristic with the control surface. Okay. Wherever it exists, you put it. Otherwise, you set it 0. So it will be like a factor you have to take. Where it exists, you should see. L1, L2. In this zone only it exists. Okay. And then the other term is, because it is rolling, I am taking the right side wing. What will happen? LP will be the velocity, normal velocity. Any LP or YP, any Y into P, divided by U. So I will have the change, it will be, because it will be like this. This velocity will be, this is my U. Okay. So this is my YP. So this is the angle. Because it gets reduced, because my aerofoil is like this. Okay, that is why the reduction comes. And then you have the twist, elastic twist. Okay. Please understand, this is for only anti-symmetric lift distribution. Now I have to write my equation of twist equation. But here, please remember this. This is induced angle of attack due to roll rate. Okay. This is, we call it, the terminology is aerodynamic twist. Okay. This is not a geometric twist. This is the aerodynamic twist of rigid wing resulting from unit deflection of aileron. Okay. This is the unit deflection of the aileron. Okay, unit angular deflection, you can take it anything. Okay, now that is the due to elastic twist. And then you will have a load factor also coming in. Now you go back and start looking at our elastic twist equation. Because the equation does not change. That is why the torsional equation for a straight wing, that remains the same. Only thing is, we have to go and then identify which are the places where I change my terms due to this. Okay? It is very important. Now your torsional equation dy dj d theta over dy. Please understand, now I am going to write QEC CL alpha into theta. I will not write CL alpha into theta. I will put it just CL elastic. Please understand, this is CL elastic minus QEC CL rigid. Okay, because my CL, I am writing it as CL rigid plus CL elastic. Okay, just for my convenience only. Otherwise I will put CL alpha into theta. Okay, but here it is not CL alpha into alpha, because it is a little different. That is why I put rigid there. Minus, you will have Q C square CM AC plus NMGD. Okay, and of course with the boundary condition, theta 0 at root and d theta by dy at the tip is 0. No twisting moment at the tip. Now here we have to see what are all the various terms. What is this? Because please understand, anti-symmetric lift distribution is a perturbation analysis. Okay, you are in a level flight, you are in a particular flight condition, you are now deflecting a control surface. What is the change? That is what is more important. Okay, the change in angle of attack is due to this. Okay, please understand, the change is this. You have a level steady, alpha 0 r will always be there. That is, the alpha r of the entire wing will exist. Over and above, what is the change in angle of attack is this. Okay, that is why we take these two terms are contributing, because they are not functions of theta. Okay, so these two contribute towards CLI. Okay, whereas this term is contributing to this. And then CMAC, I will write the expression. Okay, now what we write is CLR. Please understand, this is the change in lift due to deflection of the aileron. I will put delta CLR, delta beta into beta. This is not angle of attack, this is CL, please understand. Here this is angle of attack. I can multiply by CL alpha and take it here, and then this will become the CLR. So this will become CL alpha, alpha R, this particular factor will become this value. And then plus over delta PL over U. Please understand, I am taking PL over U. Alright, this is a full L. I am not taking only Y. This is at every point. Okay, I am taking. Now this will become PL over U. But this is a function of Y. Okay. Please understand, I am taking this variation due to a roll rate. I take the reference value as the value at the tip. Actually, this term is called the U is helix angle, okay, at wing tip. Please understand, every section will have change in angle here. Okay, I am only representing it. Yes, my lift coefficient will change at every section. Okay, but how much it will change? I am taking the reference as PL over U, which is the change in angle of attack at the tip due to roll rate. Okay, this is for just reference, PL over U. Okay, otherwise what this will be, if I take Py over U, it is a function of Y. Okay, so I am taking only one reference, PL over U, as the tip helix. And then I will calculate, this is every section, there is a, because it will be what? If I multiply by L and L, I will get this L, I can write it. This is a function. PL over U is constant. Okay, this is just varying along the span, which is my lift is varying along the span. Okay. Similarly, you will write your CMAC. This is delta CMAC over into beta, because my moment coefficient is independent of angle of attack, because this term is only angle of attack change. This is not due to camber change, whereas this is camber change beta. That is why you say CMAC is only this. Okay. Now what you write, you will go to what is N, my load factor. Load factor, because it is antisymmetric. That is why you will write this as Y P dot over G. Because P dot is angular acceleration, Y into angular acceleration is the acceleration at any point, divided by G, this is the load factor. Okay. Y P dot over G. This is the load factor at every point along the span. Okay. Now I erase this part. Now if you have a doubt, you can ask me. Okay. Now I go back and write all these things in my equation. Okay. If I write it, I have to substitute, of course, CLE is CL alpha into theta. That's all. So you can have your equation now gets modified after substituting all these things. It will become d over dy gj d theta over dy plus q e c. I can write CLE as CL alpha into theta, no problem. But right hand side minus q e c CLR is this term. Okay, I am going to put it delta CLR over delta beta. Okay, please understand, I am going to write into beta. Then you will have to write plus delta CLR over delta PL over U into PL over U, and then minus Q C square delta CMAC over delta beta times beta, and then plus M, G and G will cancel out, M Y P dot into D. Okay. Now what you can do is you can simplify this part. Okay. And then write it that is what you are doing is you are collecting the terms of beta into one, PL over U separately and then P dot separately. So you will have three terms which you will write it as d over dy of gj d theta over dy plus qec equals minus q ec delta CLR over delta beta plus C square delta CMAC over delta beta times beta minus Q E C delta CLR over delta PL over U into PL over U. plus m y p dot d. Okay. Now you have the equation. Please understand, these are all functions of y, because this exists wherever you have the control surface. Other places this will not exist. Okay. And this is full. It will exist everywhere because PL over U, y. So this term is along the full span, and this is again full. What you do is you assume now I cannot derive the equation even if it is a uniform wing, because even in uniform wing what happens is this term exists only where my control surface is existing. Okay. These things I can get solution. This is one partial. Yes, I can write it as though it exists, put a delta function and then make it. But I am going to write it only in symbolic form. Okay. Now whatever I am deriving from now on is symbolic. Just I give you expressions. This is just for information, because if you need to do, you have to do numerically, you can do for a wing. Because I got a data for a wing, we can do it, and it has to be a homework problem. Now what I do is I solve this. This is a linear differential equation. Linear differential equation with three independent quantities. One is beta, that is the control surface deflection. Another one is the helix angle at the tip, PL over U, that is basically roll rate. Third one is roll angular acceleration, which is the rate of roll rate. Okay, P dot. Now my solution because you can put the boundary condition. Please understand, you have put the boundary condition theta at 0 is 0, d theta by dy, tip is 0, free tip. Then I can write my solution as, I am going to write it only in symbolic, C1, which is a function of y, some C1, okay, which will be some part of homogeneous plus this into beta, plus C2, another function of y into PL over U, plus C3, which is another function of y into P dot. Okay. Okay, this is my solution. Taking into consideration after boundary condition everything, this is my okay. Now I can go and calculate what is my CL. Okay. Because CL consists of two parts. Please understand. A rigid part and an elastic part. You remember the elastic part, rigid part, what I meant is, that is rigid part is this part. Okay, CL, this part is the rigid part. This is an anti-symmetric problem, please understand. But then my theta is again a function of beta and PL over U, and as well as the P dot. That means if I substitute in my CL, this term I will substitute as it is, and then in the CLE, which will become this term. Okay. So I will write, because again I am writing it in a symbolic fashion. Okay. That is why these problems are a little involved. So you have your CL consists of CLR and then E. And CLE is CL alpha times theta y. Okay. Whereas your CLR is what we wrote as the earlier expression. Okay. Now let us write our full expression and then write it in a symbolic form. Okay. CLR y is basically theta beta beta. This is again a function of y, because some point it will be existing, some point wherever the control surface is not there, it will not exist. Plus PL over U into PL over U. This is my CLR. Whereas my CLE is CL alpha times C1y beta plus C2y PL over U plus C3y beta. Okay. Now I have to add both. So we can add both of them. You can get the full CL expression. Okay. Now with this we can solve. I erase this part. Please understand. 3 types of problems. Okay. 3 types. You can also, because I will explain. One is sudden deflection of the control surface. Okay. Then what is the resulting effect? That means sudden deflection is, you can say, a step input to aileron deflection. What is the resulting effect? Okay, this is one problem. Then because of that, what is the change in the lift distribution? Please understand. I give a sudden thing. What is the change in my lift distribution? CL along the span. Because CL, C into CL, Q dynamic pressure, I will get the lift distribution. This is one problem. Second problem is, I will say, if you have a steady roll rate. Number 2, a steady roll rate P. Okay. What is the lift distribution? See, all of them require basically what is the type of lift distribution in each case. See, initially it is flying, you suddenly deflect, how my load is changing. Okay. Another one is, this is one problem, steady roll rate P. And of course third one is control effectiveness and aileron reversal. Control effectiveness and aileron reversal. Okay. These are the 3 types of, you can say, the problems which one analyzes with this solution. Okay. Now, first we will go step by step.
So,
Yeah.
one question. So this quantity P we are treating is as an independent variable.
Yeah, P is an independent variable.
But sir, P will depend on what is
Yes, that's what.
on
What
the-
I am saying is I am having a roll rate. Because of that roll rate, I have an angle of attack change. Okay. How I generate that is different. Okay.
I don't care.
How I generate? I have to generate by deflecting the. Yes. But if I have this much roll rate, what is the angle of attack change? Okay. Now, what you asked, that question will be answered. Now, if I deflect this suddenly, initially the aircraft is level flight. I am deflecting it. At that time, when you deflect, what happens? Your roll rate is 0. Okay? Because you have generated a moment, you will have only roll acceleration. You will not have roll rate. You are starting. That is why an F is, according to Newton's law, F is ma. Similarly, moment is I alpha. So I will have a roll acceleration. So what you have to solve is, first problem, if you take, but my roll velocity at that instant is 0 when I am starting. Then you can integrate it, how the roll acceleration changes with time, then you can get the velocity, etc. Okay? Now we will write it in a simple form. Maybe I take this lift distribution due to, I will write here lift distribution due to a step change. So what you have done is you have suddenly put a aileron. What happens? You generate actually, if you say Ixx is the roll inertia of the vehicle and P dot is the roll acceleration. This is what the effect. Now this must be equal to what you have generated, because the two wings you have to take, that is why it is anti-symmetric, so I am taking 2 times Q dynamic pressure 0 to L C CL Y dy, but this CL is written as okay with what? P is 0. Please understand, P is 0. Sudden deflection. There is no roll rate at that time. So I can go back, substitute for CLR. Only this term will come because there is no roll velocity. So this is gone. And I have, this term is gone. But P dot is existing here. Okay? So that will come in the integration. So what we can do is, maybe I go to this section. We will write it in a form which is, I am going to use some symbols. Okay? Because you can put it, substitute this expression there. So you will have what? Ixx P dot equals 2Q integral 0 to L C, okay, into CLR is into beta. That is the first term. The second term will have CLE term. CLE term will be plus what? Cl alpha C1 y beta, this is not there, plus, because Cl alpha is common, so I will have to take Cl alpha C3 y p dot into y dy, right? Now this is p dot. Okay, I can take this term on the left hand side and then take out the p dot outside. So I will have p dot into Ixx minus 2q integral 0 to L C Cl alpha C3 y dy, okay, equals, you will have 2q integral 0 to L C delta Cl r over delta beta, because this is also beta dependent, okay, plus you will have C Cl alpha C1y into y dy times beta. Alright. Now you see, I can get p dot in terms of beta. Okay. So this will be, I just have to divide this by the right hand side. I will have p dot is equal to something times, that is the numerator expression is this, denominator expression is this, into beta. So this is my p dot, okay, which is a function of beta. Once I know p dot, I can go and put it p dot as a function of beta. Okay, that means I will know CLE, I know CLR, okay, I can immediately get CL, which is I can get the full lift distribution if you suddenly give a beta. Okay, now you see, this is how the calculation is to be done. The next problem, which is actually the lift distribution due to steady roll, if you take it, steady roll means what? Moment is 0. So that problem you need to write it in this fashion. So lift distribution due to steady roll, that means P a constant, okay. Which means my moment, if I integrate 2, because basically the load on one side must balance the load on the other side, because I have a steady thing. This is 0, 2q, because this is my roll, because lift into y, okay. My roll moment is 0, okay. Now how do we do? Which means you integrate 0 to L, 2q, anyway it is a steady dynamic pressure, so that can be thrown out. You will have C CLR y dy plus integral 0 to L C CLE y dy is 0. Now you substitute the two expressions here with P constant but P dot is 0. Okay. Then what will happen is, I will write it here. So P is a constant there. So you will get CLR is beta. Okay. And then what do you get? That you will get beta term. You will get a beta term here. You will get a PL by Y. You will have these two terms. And then what you can do is you can take beta separately and then PL over U separately. Then you write beta equals PL over U. Okay, so now we will write it. What is the first term? Integral 0 to L. CLR is C delta CLR over delta beta to beta into Y dy plus you have again C delta CLR over delta PL over U into Y dy. Okay. This is the first term. And the second term CLE will be plus integral 0 to L C into CL alpha. I have to put C1Y beta plus C2Y PL over U into Y 0. Okay. Now what you can do is combine the beta term, combine the PL over U term. Okay. And then take two terms outside. So what will you have? You will have beta times. This is the first term. Integral 0 to L C delta CLR over delta beta Y dy. Okay. Plus this term C CL alpha C1Y into Y dy. This integral is there everywhere, y dy, y dy. That is why that integral should be every time. This is equal to, you put a minus sign. This is PL over U. Again open, integral 0 to L C delta CL R over delta PL over U. This is the first term into Y dy plus this term C CL alpha C2 Y Y dy. Okay. Now what you can write is beta to steady roll rate. If you want to have a steady roll rate, what should be the angle? Okay. Now this you can write it in. I will write this expression because this is the expression which is required later. Okay. I will write here minus 0 to L. You can C delta CLR plus C CL alpha C 2Y into zero to L C delta CL R over delta beta plus C CL alpha C1y into y dy. Okay. This is my expression for if I have a steady roll rate. That is, if I want to have a steady roll rate, what should be my deflection? Okay, this gives me the deflection. Now the third problem, which I said aileron effectiveness. Okay. Third is aileron effectiveness. This essentially comes from that expression. Okay. Because I take this term, and what you do is you divide by beta. Okay. That is for a unit aileron deflection, what is the roll rate I get? In the sense, I am basically writing the expression like this: PL over U over distance beta. So this is basically inverse of that. That will become what? Even if I take this is a linear relationship, you will have minus. You will put little minus sign. You can take it here. You will have 0 to L C delta delta beta plus you will have C CL alpha C1 C1 sorry C1
Yes, sir, C1 y.
C1y, right?
Yes, sir.
C1y into
Y dy.
y dy over 0 to L,
C.
the other,
Yes, sir. C.
which one? The first expression, right? C
C.
delta
CL
over delta
PL
PL over U plus
C into CL
C CL alpha
C2y.
into C2y over C. Okay. Hey, wait, 1 minute. I'm just checking. Is there a, you have a, this is a lift coefficient, right? CLR. Okay. C into lift coefficient. I'm taking QC CL. Now you see here any deflection of this. Okay. If this is 0, that means I don't get any roll rate, which means aileron is ineffective. So the speed at which the numerator is becoming 0 is my aileron reversal speed. But other places, because of if it is a rigid aircraft and if it is a flexible aircraft, okay, please understand, rigid means you will have only this term, right? Because of flexibility, what happens? This term has come into picture because of flexibility. Okay. Not only that term, this term also has come into picture. If it is rigid, you will have only these two. Because it is flexible, you are going to have these two terms. So the effectiveness of aileron, if you consider a rigid aircraft, you will get one rate for a unit deflection of this. If you get a flexible aircraft, for the same unit deflection of the aileron, you may not get the same roll rate. Okay. Now, this is aileron effectiveness. and the speed at which, no matter what you do to better,
Yes.
if it is not happening, and that is numerator 0. Now when you increase the speed, the dynamic pressure or whatever, maybe because that dynamic pressure is going to change any of these values. At that speed what will happen is numerator becomes negative. Then what will happen? Your aircraft will turn the opposite. Okay. So your aileron effectiveness is part of this problem.